First, always master one technical domain deeply. The credibility that it builds, it compounds over time, exponentially. Second, always learn to think in constraints. Think about budget, people, timelines, not just equations. In the long run, perfect technical design rarely makes it out of the door. Third, always practice translation relentlessly. The ability to move between engineers and decision makers is what turns good ideas into funded programs. I believe a lot of the roles, the niche that I have earned over years is only because I have been able to communicate the right language with the right people. Leadership is not about leaving engineering. It's expanding the impact and working with both leaders and engineers as part of this process.
Today's guest is at the foremost of the transition, Anushree Ramanath. Anushree is an electrical and computer engineering expert whose work bridges the gap between the complex power systems and the hardware that makes them a reality. She's also an author, innovator, linguistic, and an artist. Today, we are talking about the brain of the modern power grid and the reality of moving research from the lab to the real world. Welcome to PMP with Prachi. Today, we are diving into the literal current that powers our world. As we shift towards a greener future, the grid is becoming more smarter, more complex, and more digital. And today's guest is at the foremost of the transition, Anushree Ramanath. Anushree is an electrical and computer engineering expert whose work bridges the gap between the complex power systems and the hardware that makes them a reality. From her early days as a top student and software engineer to PhD, her deep dive research into fuel cell emulators and cyber physical systems at the University of Minnesota, Anushree has a unique perspective on how we build the energy infrastructure of tomorrow. But beyond the circuits and the code, she's also an author, innovator, linguistic, and an artist. Today, we are talking about the brain of the modern power grid and the reality of moving research from the lab to the real world. Anushree, it's great to have you on the show.
Thanks, Prachi. It's a pleasure.
Yeah. So why don't we kick off by hearing from you a brief introduction about yourself and share the key pivot points in your journey from software engineering to leading work in advanced energy systems in the US.
Absolutely. I currently lead work at the intersection of data analytics and advanced energy systems in the US, focusing on power electronics, controls, and AI, the way they come together to run the real world energy infrastructure. Things like residential solar, batteries, EVs, and all our grid interactive systems. But my journey did not start with sustainable energy systems. I started as a full stack software engineer in Bangalore, India. Early in my career, I was close to production systems, release cycles, and customers who felt the impact of even small defects. That environment trained me to value reliability, timelines, and ownership very early on. The first major pivot came when I realized I was increasingly drawn to systems where software alone was not enough, where physics, uncertainty, and real-world constraints shaped outcomes. That led me to pursue a PhD in electrical and computer engineering, where I moved into power electronics, energy storage, and control systems. Suddenly, the bugs did not just crash programs, but they could damage real hardware and destabilize real-world systems. The final pivot was returning to the industry in the US, where the challenge was not just innovation, but scale. Translating lab-grade models into field-ready, compliant, and economically viable products required a completely different mindset. That progression from writing code to building models to now scaling systems, I feel that's how I define and lead complex multi-year technical programs.
Mm-hmm. And I don't know many people who have double masters and a PhD. Uh, that's really fascinating, Anushree. Uh, when you move from PhD level models to industrial products, how do you structure the phase gate from simulation to hardware so that risk, cost, scope stays under control?
When moving from PhD level models to industrial products, I don't see it like a linear trade off. I treat it more like a structured risk retirement funnel. In early simulation, the goal is not performance, it's only validating our assumptions. I spend a lot of time on sensitivity analysis, edge cases, understanding what parameters the system is truly fragile to. Now, in the next phase, we try to introduce realistic aspects, your non ideal components, real communication delays, sensor errors, and so on. This is where most of the designs fail quietly if teams move fast without consideration into these. Then comes the limited pilots, like small scale deployment with real actual users. At this stage, instrumentation matters much more than optimization. We are learning how the system behaves, but we're not yet trying to perfect it. Finally, it's the scalability. When we are at the gate for scalability, we think about all the cost curves, the supply chains, firmware update paths, regulatory compliance, and here optimization is the key. Overall, if we look at it, the key leadership principle is we advance phases only when we have retired the unknowns, but not just when the results look good.
Yeah, and that's typical for a waterfall or traditional approach of project management looks like in such a industry where you have to be precise. You can't just be agile. So, talking about risk, cost, and stuff, let's talk about schedule. As a researcher, you work on first of its kind systems like fuel cell emulators. For a program manager trying to build a schedule around those innovations, how do they balance the deep work needed for a breakthrough with the milestones required by a project plan? How can a PM tell the difference between the technical roadblock and the lack of progress?
When we're working on first of its kind systems, like for example, multi day storage batteries, the tension between deep technical work and project milestones is very real. Breakthroughs don't arrive on predictable cadence, but programs will still need schedules, forecasts, and accountability tied to it. The way I balance this is by separating deep work from visible progress. Deep work, whether it is discovering a new degradation mechanism or validating a new control strategy, all of this needs protected time without any artificial deadlines around it. But this still does not mean it's invisible. The way I structure it, I try to work on innovation around learning milestones, but not really on feature milestones. Instead of asking, did we hit this amount of performance? We try to ask, what uncertainty did we retire from this sprint? For example, in early multi day storage research, we may not improve efficiency at all for multiple weeks at a stretch, but we might conclusively prove that a particular failure mode cannot be mitigated. That is real progress. For program managers, the key diagnostic question in this is, are assumptions getting sharper over time? If models are becoming more constrained, experiments are becoming more targeted, and the decision paths are clearer, even without a breakthrough, that's a technical roadblock being worked through responsibly. A lack of progress, on the other hand, it feels different. You will see repeating experiments, vague explanations, no change in the risk profile. It's very easy to say one from the other at that point. Breakthrough work will need protected depth, but progress will still show its footprints. Eventually, along the path, a good program manager will learn to track those footprints and understand how genuine the contributions are.
Mm-hmm. Yeah, it's actually true that eventually you will learn. It's not just when you are doing the project. Even though we have done the similar project in the past, it's just the experience over experience you build, and then you learn from those experiences. And oh, even though the developer or your team member is saying so and so timeline, I'm sure it's not going to be done by that timeline, and you add a buffer to it. So it's just by experience you calculate that risks and schedule. So again, talking about the risks, you have written about the impact of cyber physical systems on the energy transition. These systems introduce massive security and integration risks. So when a PM is looking at the project's risk register, what are the invisible technical risks in power electronics that we often overlook until it's too late?
The cyber physical systems can absolutely introduce new security and integration risks. But in power electronics, the most dangerous risks are often invisible until it's very late. One of the common blind spots is the timing and synchronization risk. The control algorithms may be secure and they might be mathematically sound, but when it's deployed across real systems with network latency, jitters, clock drift, you can trigger instability that never appeared in simulations. Another overlooked risk is component interaction and or some of the rare environmental conditions. Power electronics often behaves beautifully at nominal loads, but at low probability combinations. Cold weather, partial failure, grid disturbances, all of these small nonlinearities end up cascading. Another invisible risk is the coupling between our firmware and hardware components. Even a minor firmware update can unintentionally stress our hardware components in ways that the original thermal or lifetime models never can anticipate. For PMs who are thinking about reviewing a risk register, I always recommend them to ask what assumptions rely on ideal timing. What happens if some of these sensors do not give expected results briefly? What degrades slowly rather than fails fast? I think that's a very important one. The most dangerous risks, they don't fail loudly, they just degrade quietly. And those are the ones that derail the schedules the most.
Hmm. Yeah, and also it impacts the technical debt. And in your article of EE Power, you broke down complex topologies for the industry from PM's perspective. Technical debt often happens when documentation lags behind design. So, what's your best practice for ensuring that complex engineering changes are captured so next project manager isn't left with the mystery for
You're
especially.
absolutely right. Yeah, you're absolutely right. The technical debt often comes when documentation trails complex engineering changes. I've seen brilliant designs that become liabilities simply because the rationale was lost. My best practice is to document decisions, not just the changes in design. So, whenever a topology changes, or for example, a control strategy evolves with time, we capture three things mainly in a living document: what changed, why it changed, and what trade offs were explicitly rejected. This does not need to be heavy. In fact, the more brief and short it is, the better. One page per major decision that actually beats hundreds of pages of static documentation that lies around unupdated. I also insist on design review notes being archived as first class artifacts, not just as minutes of meetings somewhere lying around. Future project managers don't need to rediscover history, they need to understand the intent. So it's very important to be very precise, crisp in our summaries, and more so document everything that led to a decision, including the assumptions, some thought processes, things that we debated and thought selected one over the other. If a design decision is not documented, it is technical debt. No matter how elegant it looks on hardware, it's still not complete.
I so agree. And you mentioned about precision and documentation because nobody likes to go through those heavy documentations. And there's no point writing these many documentations if nobody is referring to. So, being precise and writing the decision why it worked and why it didn't work is important for future projects. Um, and it also, along with documentation, you should also be good at communication and not silo. So, you speak four languages, but the fourth one is engineering speak, what engineers speak. When a PM who might not be a PE sits in a room with hardware teams and a firmware team, how can they facilitate better communication between these two silos? Where do these two groups usually misalign?
True, engineer speak is a language of its own. And the hardest translation gap that I have seen so far is between hardware and firmware teams. Hardware engineers mostly think in continuous domains. Think of voltage, temperature, tolerance, physics. The firmware engineers think more in discrete terms: timing loops, logic paths, different states of the machine. The problems mostly arise because each side assumes that the other understands their constraints implicitly. For PMs who are facilitating these discussions, I think the most effective way is to move to anchor the conversations around interfaces, but not the implementations by itself. You can ask questions like, what signals cross a particular boundary? What assumptions does each side make about timing, accuracy, failure, and critical key parameter indices like this? What happens when those assumptions are violated? When teams misalign, most often it is around edge cases like your startup, shutdown, faults, and even some partial failures. Everyone designs for steady state, but real systems, they live in transitions. A PM does not need to be a PE to bridge this gap, essentially. They only need to slow the conversation and make it very specific and grounded enough that the assumptions become more explicit in nature.
So, being explicit and finding edge cases beforehand helps a lot. And communicating in simple words rather than jargons, it helps again better communicate and managing the project. For a technical leadership audience, how do you describe cyber physical brain being built to run future grids? And what does that mean for how we manage portfolios of energy projects?
I often describe the future grid as shifting from hardware first system to more of a software orchestrated organism. In this scenario, sensors act like a nervous system. Power electronics and storage can be perceived as muscles. AI control algorithms form the brain of it. What this means is it can help in coordinating millions of distributed assets in real time. For project and portfolio leaders, this changes everything. Projects are no longer isolated assets that are delivering standalone return on investment. Value will increasingly come more from coordination, that is, how assets can work together across time and geography. That means the portfolios must be managed for flexibility, for system level resilience, and not just for individual asset performance. That's how we can work with the physical aspects of the cyber security systems.
Okay, and working with the real world data, what has most surprised you about how people actually use their solar batteries and EVs day to day? How has that influenced your view on what's good system design looks like?
One of the biggest surprises from real world data is how differently people behave compared to our model's assumptions. EV charging, for example, it's often driven by emotion and habit, not really by economics. People charge when it feels safe, not when it's the cheapest. Many users ignore the time of use rates entirely if the system requires more manual effort. This has reshaped my view of good system design. The best systems minimize user decisions, they automate the complexity, and they respect human behavior instead of trying to correct it. From a program perspective, the most successful technologies are the ones the users barely notice.
Wow, wow, that's a lovely perspective from the eyes of somebody working in that industry and from the customer's point of view. So that's interesting. Uh, and among the residential clean energy technologies, what is one area you think is quietly transformative but still underappreciated? For example, the advances the in behind the meter analytics, flexible load control, or home energy management algorithms, and why should technical leaders be paying much closer attention to it when shaping their roadmaps?
One quietly transformative area is behind the meter intelligence. It has adaptive control, it has analytics that sits on top of the existing assets. These capabilities are a little less visible than hardware. It's harder to demo, and it is extremely cross disciplinary, which is why they're probably often underappreciated. But they turn these static assets into dynamic resources. It helps in enabling aggregation for grid services, and they dramatically improve resilience without adding new hardware. For technical leaders that are shaping roadmaps, this is where return on investment compounds quietly. Intelligence multiplies value without actually increasing the physical complexity, and that's the dream of every innovator.
And finally, I would like to wrap it up by asking you, looking back to your research assistant days, what advice would you give to engineers who want to grow into project program or portfolio leaders in technical domains?
Looking back at my research assistant days, my advice is very simple, but probably it's hard. First, always master one technical domain deeply. The credibility that it builds, it compounds over time, exponentially. Second, always learn to think in constraints. Think about budget, people, timelines, not just equations. In the long run, perfect technical design rarely makes it out of the door. Third, always practice translation relentlessly. The ability to move between engineers and decision makers is what turns good ideas into funded programs. I believe a lot of the roles, the niche that I have earned over years, is only because I have been able to communicate the right language with the right people. Leadership is not about leaving engineering, it's expanding the impact and working with both leaders and engineers as part of this process. It's extremely important that we think about scale, we think about not shipping perfection, but we have to ship reality. That's when we can bridge the gap between the industry and our academia.
Yeah.
I feel that all of the perspectives that we have in terms of perfect design, initially it needs to bridge the research, the productization, and the program execution. That's the only path to success.
And it almost boils down to soft skills, having good soft skills. And of course, the background knowledge, of course, it helps a lot, like technical background. But then once you have that technical background, if you don't have the soft skills, try to develop it. So again, in the real world, it all boils down to soft skills. All right.
Absolutely.
Before wrapping up, I have a quick 10 seconds hot take for you. So, in just few words, okay? This should be fun and quick. All right. The first one, will we ever actually see flying electrical cars?
Yes,
How soon? 5, 10
few
years?
decades, probably 2 decades.
Yeah. Okay. Cool. Is smart home tech actually smart or just annoying?
It is smart, but it does test your smartness.
True. Is using AI to manage the grid a massive security risk we aren't ready for, or is the grid too complex for humans to manage alone?
It's a bit of both, but till we master the ethical and secure side, it's hard to implement at scale. So it's a tough balance. We need to learn to implement and also balance out the security aspects along the way.
Great. And finally, engineers love to perfect a design. As we mentioned in our episode again and again, but PMs need to ship a minimum viable product, that is the MVP. In energy systems where safety is paramount, is good enough a dangerous space, or do researchers need to be more comfortable with the 80/20 rules?
Industry taught me to ship reality, but not perfection. It is important to be safety aware for sure. It's not negotiable only because we are dealing with systems that sit in people's home, probably under a kid's bedroom, on the side of someone's living room. So there's no way we can compromise safety, but the perfection in the aspect of having the best efficiency, utmost reliability, they are work in progress for sure. And it's important to focus on a product that's usable in a tangible time frame than perfect it to nth quality and not have a way to launch it.
Thank you. Thank you for sharing your valuable insights and sharing your journey from software engineer to the cutting edge of energy research. If you are a student looking to make that leap into research, or just someone curious about how our world stays powered, I hope this conversation sparked something for you. As always, you can find link to Anushree's work and her technical articles in the show notes. And thanks for watching and listening, and we will catch you on the next episode. Thank you so much. Bye bye.
Bye bye.